अस्सलाम वालेकुम। अभी थोड़ा सा टाइम है, so I'm just trying to set up how much. डॉक्टर अली भी सेटअप कर रहे हैं। आई थिंक देर में वी कैन जस्ट yeah, not bad. Not bad. So today we shall be learning about application of decimation. As I mentioned the previous day, that decimation is used in many applications, and the whole purpose of decimation is that you are reducing the size of the signal, and this reduction is done by first passing the signal through a low pass filter and then throwing away samples. So for example, here you see this is an image. So you pass every column of this image through a low pass filter and then throw away every sample. So the image will be reduced into half. So this is the half image. Okay. And then you pass the same image through a high pass filter, same image through high pass filter, and again do the same. Throw away every other sample. So this image will also be reduced by half. And then is you have every row is passed through a low pass filter and you throw away a sample. Once you throw away a sample, definitely the image will reduce into half. And same you do with passing image through a high pass filter, image will be reduced into half again. So if you do this successively, these operations successively, what you are going to see is an image. So what you see is an image which is this is what you see, an image which is reduced into 1/4. So first you pass every column through a low pass filter and throw every other sample, then you pass every column and you throw every other sample. So image is reduced into half, 1/4, half in rows and half in column. So this is a decimated image. Okay. And similarly, you see three other images here. And these images are that you are passing it through a high pass filter and high low pass filter. So I'll be drawing this, but important is this image again. So this is the image which you get after you pass it through a low pass filter every row, then a low pass filter every column, and throw every other sample. And remember, you are seeing 4 images, 1, 2, 3, 4 images, but just focus on the above image. Now you take this image and again do the decimation. Once you do the decimation, so this is the original image. So you do the decimation once, you get this image. Then you do the decimation 2, you get this image. And you know the decimation 3, you get this image. Very little image, what you see there, a small image. Okay, here. So this is passing successively decimation. So we use this in machine learning, pattern recognition, where if we intend to recognize an object instead of working on a full scale image, this will take a lot of time. We work on a smaller image, this. And if we see an object, only then successively we can work on a little bigger image, or even a bigger image, or on a full scale image, So we can reduce the amount of computation by just working on a small images. And if we see that there's an object, and now for example we are just detecting a specific type of a vehicle, let's say motorbikes. So first we need to see whether there is a vehicle in a frame or not. So instead of working on a full scale image, you can work on a very small scale image and see, yes, there is something. And once there is something, now you need to figure out whether it's a motorbike or a car. And then either you can directly move to full scale image, or you can successively go to bigger images, and then you decide whether the image is small, or whether there's an object in it or not. Same is the case in in artificial neural network or deep learning, and you must have heard a lot about machine learning. This is me at Georgia Tech, working in the lab of the control of highly uncertain systems. And this is my first publication, and this publication is on न्यूरल नेटवर्क्स. और ये मैंने एक शेर भी लिखा है, सुना सकता हूँ मैं, कि तस्वीरों तितलियों से रंग लेकर जुगनुओं से रोशनी, हम ख्यालों में बसा रखते थे एक दुनिया नई. The old days. So this is my first publication which I presented, and this paper on neural networks at MIT Lincoln Lab. And so in deep neural networks, we also use decimation a lot. And decimation means that you primarily pass it through filters and then throw away samples. And you keep doing those samples to find low-level features, mid-level features, and high-level features. Okay. So this I have already shown you, convolutional neural network. In convolutional neural network, what we do is that we pass an image through many filters or masks. For example, if we intend to detect an X in an image, so we may have multiple features. As you can see, there are diagonal lines, there are crossing lines, and so you decide about all the masks or filter you need to use for this. So these are some of those masks. So these are the filters to detect the diagonal line. 1 1 1 1, this 1 1 1 1 1. So this will detect this. This 1 1 1 1 will detect this, or this 1 1 1 1. So these can detect this line, and so you have an image and then a series of filters where you convolve and get a series of images. This is important. Okay, so you have multiple filters, you apply those filters, and these series of images, then you decimate to make smaller images. And this operation in deep learning is called max pooling. Max pooling is an operation where you have an image and then you decimate. So just telling you an application of decimation in deep neural networks, where we use convolution and then decimation. And then you pass it through a fully connected layer. This is a fully connected layer. So an image, let's say it is, then you apply filters, and then you have series of images which you put in a cube. So depth will tell you how many images do you have, and it also depends upon that how many filters do you have. And so this is the size, and this is how the backpropagation neural network works. So once you apply a filter, this is something you're going to see. Okay, once you apply a filter on an image, may it be a high pass or a low pass filter, then there is an operation in deep neural networks which is called ReLU, which means a rectifier linear unit, which primarily does nothing, but just if there is a negative value, it will make negative value equal to 0, because in images negative value does not mean anything. Only we need to work on the positive values, and each positive value is associated with a grayscale. So rectified linear unit primarily converts all the negative values to 0. So this is an image, and once you have rectified it, you get this image. So this is the process of decimation. Decimation means that you are reducing the size of an image. So every 2 by 2 block will be converted into 1 pixel. So there are a number of ways of doing that. One is just you systematically throw away samples. Keep this sample, then you keep this sample, then you keep this sample, then you keep this sample. So this 4 by 4 will be reduced into 2 by 2. The second method is that you take maximum of these. You take maximum of these 1, 1, 5, 6. What is maximum? 6. So you take 6. In the green block, it is 2, 4, 7, 8. What is maximum? 8. So you take 8. Then you have 3, 2, 1, 2. What is maximum? 3. So you take 3. And then you have 1, 0, 3, 4. So you have 4. So this is a reduced, a decimated image. So you find a decimated image by the operation of pooling. Pooling will give you a decimated image. So this is where you are, once you are doing decimation, you're getting smaller images, then you do further decimation, you get mid-level features, then you do further decimation and image is reducing into size, and you see high-level features. So in deep neural networks, you have multiple masks, and in every stage, you keep decimation, and once you are decimating, as a matter of fact, you are automatically detecting low-level features, mid-level features, and high-level features. So this is how the neural network works. So for example, here you have this input image, and then input image is passed through a number of filters. Once you pass it through a number of filters, so you get a number of images. So that's why it is shown as a cube. And then you decimate, throw away samples. So same cube will be reduced in size, it'll be smaller cube. And then you again pass it through a series of filters. Okay, and then again you reduce size. So you're smaller. So you reduce size, and then keep doing this, and at a stage you have a fully connected neural network, and then basically you detect whether the object is a car or a truck or a van or a bicycle. So the deep neural networks heavily use convolution and decimation operation. So this is a complete deep neural network that uses decimation throughout successive decimation, and then there's a fully connected neural network which basically writes 1 into one of these array. Whether the first one, if there is a car, it detects a car, it will put a 1 here, and rest will all be 0. If it detects a truck, it will put a 1 here in the second location, and rest will be zeros. So this is another interesting application of segmentation, scene segmentation, where you have to figure out whether a pixel belongs to a sky or a building or a pole or a road marking or a pavement or a fence or a vehicle, So these are the different classifications which you need to do on every pixel. So how you do that? Again, the same, that you have series of filters and you keep decimating, decimate. And this is an interesting example because after doing many decimations, you go through interpolation. So convert the image back into the size it was originally. So you have a video. So video has multiple frames. So you're getting frame, and then you decimate. And so the scene, after you do a series of decimation and interpolation, this is how the scene is going to look like. You see that now, and interesting is if I run the video. So this is again the segmentation where you are detecting people. The person standing there are being detected. Okay, trees are detected, roads are detected. And let me run this. You see? Wow. So every frame you are segmenting using deep neural networks. There is a house is colored differently than, so The lines on the road are being segmented, and the trees are segmented with different color, and this is done through a series of interpolation and decimation operation. So interpolation and decimation plays a key role, as I mentioned earlier, in machine learning, pattern recognition, image compression, and many other applications. So decimation and interpolation plays a critical role. If you look at this, this is again important. Just remember that an image is broken down, and this is how the JPEG works. This is all your cameras work, the smartphones, the cameras in the smartphone works, that they are automatically doing these operations. That they're passing the image through many filters and then dividing an image based on their frequency information. This image has low frequency information. This image has high frequency information. And let's see that how it works on a piece of paper. Now let me put my camera back to. So I showed you an image. So an image is passed through a low pass filter, and the same image is passed through a high pass filter. Okay, let's say every row of the image is passed through a low pass filter, and every row is passed through a half pass filter, and then you decimate it into half, throw away every other sample. Once you throw away every other sample, image will be reduced into half. If every row is being passed, so image will be reduced into half. Okay, then you again take this image, pass it through a low pass filter, and take this image, pass it through a high pass filter, take this image, pass it through a low pass filter, take this image, pass it through a high pass filter, and now every first column is passed through a low pass filter. Once you do this, so this will be reduced into a small image like this. Originally it was like this, and this image will be called a low and a low image. Similarly, this image which passed through a low pass filter, and then you are decimating by 2 also, decimating it by 2 also. So this image will be called a low and a high image. Okay, and so you place this image here, low and high image. This image, after decimation by 2, decimation by 2, is called a high-low image, and this image is called a high-high image. Okay, so an image of size L by L will be divided into 4 images. One is an image which is a low image, another is an image which is a low-high image, another is an image which is a high-low image, another is an image which is a high-high image. And I have shown you these 4 images where you vividly see an image as a low, because images usually have a low frequency information. So image will be visible here, and rest you will find edges. These are high, so you only find edges in horizontal and edges in vertical. So edges. Now you take this image and further pass it through the same structure, this a low and a low and a high, then low, high, and a high, low, and a high. So this image again, once you do that, so you have low, high here, high here, high, low here, and this again is divided into 4 smaller images. This image is low, 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 low. This image is low, 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 high. This image is low, low, high, low. This image is low, low, high, high. See that? Now the same image is divided into 1, 2, 3, 4, 5, 6, 7 images. Then you again take this image. Okay, this is what your camera does. All the time your camera is doing this. And that's how it converts it into a JPEG image. A JPEG 2000 actually does this. So you have 4, then you have 4, then you again have 4. Then you take this image. Okay, this image. And then you keep doing this operation until you get just a pixel left, So here, the most important information in an image is a low, 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 low. This piece of information is the most important because it makes you perceive this as an image. Even this information is lost, like high, high, still it will not make any difference. You will still able to perceive that this is an image. Perhaps it will lose its fineness, like you find very nice edges, but it will not actually still make you understand that what this image is all about. So you can just throw away this part of the image if you want to, or you can just quantize it with a high coefficient. You quantize. So once you are doing JPEG compression, you move from this corner, so which is the top left corner, to top right corner, and keep increasing the quantity, keep throwing the information in this order. So you are less considerate in this portion of the image, and you are more considerate in this part, which is an important piece of information. That's how you do image compression. So you can reduce an image by 10 times or 20 times because of first passing this image and doing a series of decimation steps. So do decimation. And once you are reconstructing, you go through an inverse process of interpolation. So from here you go here, from here you go here, from here you go here. So you do decimation and you do the interpolation in image compression as well. So decimation and interpolation are two very, very important operation. We are understanding their importance, that interpolation and decimation. Are important operation in signal processing, in image processing, in deep learning, in pattern recognition, So in all these, and as I mentioned, that is part of every mobile phone, every DSLR camera, that it is doing the interpolation and decimation in order to do good compression on an image. And so these are some very, very important operations in signal processing. So in decimation, if you remember, we discussed that decimation is just throwing away of samples, and you only throw away samples if last time we did this, that you have, this is if pi over m minus pi over m, amplitude is 1, and this is a replica at 2 pi, this is pi, this is minus pi. So usually your spectrum will look like this, okay? And this gives you the comfort that you are basically can throw away samples. And if you remember, we basically studied that in decimation, you multiply this by m. And you divide the amplitude by m, okay? And you focus only on this part of the spectrum. From minus pi to pi, you do this operation, you multiply the spectrum by m. So if m is equal to 2 with 2 and m is equal to 3 with 3. And so once you do this, m cancels with m, m cancels with m, and you have a full-blown spectrum that goes from minus pi to pi, and amplitude is 1 over m. Then you make copies of this spectrum at every 2 pi minus 2 pi. Okay, you make copies of it at this and this. So your primary focus is a spectrum from minus pi to pi. So once you are doing decimation, these are the two steps which you perform. And if the spectrum is not at pi over m, okay, let's say this is 2, and you try decimating it by a factor of 3, then it will alias. Last time we have seen it, that this is an example we did last time as well, that if your spectrum look like this, okay, and what you do is that you decimate it by a factor of 3. So definitely you're going to alias this signal, because this gives you the permission to throw away only every other sample, to decimate it by 2, and you are trying to decimate it by a factor of 3. So what will happen, that your signal will, so once you multiply it by 3, you multiply it by 3, it is 1.5 pi, so it's going to be on here. So this is 1.5 pi, and this is minus 1.5 pi instead of pi and minus pi. So once you make a copy at 2 pi, so aliasing will happen. So this you must never do. So you got to be very cautious once you are decimating a signal, that you need to make sure that you are not disobeying Nyquist in any sense. So Nyquist has to be obeyed, and obeying Nyquist means that you got to be very particular about the value. You got to plot your spectrum. So take FFT to the amplitude of the spectrum and see the extent of your spectrum from minus pi to pi, and then decide at what rate you should decimate. And the second thing which I told you, that if you have decided, okay, in many applications, purely because of the cost of the system, you decide not to keep values of the signal at higher frequencies, okay. And I gave you an example of a telephone exchange, a CD quality music being played on a telephone exchange. Telephone exchange only samples signal at 16 kilohertz. So the telephone exchange has decided. Why? Because of the cost. It has decided, once they were developing the standards, they said a voice will only be sampled at 16 kilohertz, period. And every sample will be 8 bit per sample. So once you have 8 bit per sample and you have 16 samples in a second, so multiply this. So you get the sampling rate, 8 kilohertz, not 16 even, 8 kilohertz. So you have 64 kilobits per second. So a telephone exchange, if you learn about simple old digital telephone exchanges, what they do is, from your home, there is a copper wire that goes and to a telephone exchange. So an analog voice goes on this copper wire to the telco, and telco has so many lines are coming, bundles, so many copper wires. So this earth has tons of copper wire embedded in it because of the telephony. So all these copper wires going under the ground and reaching to the telco. And the telco first thing the telco would do is that it will sample every voice into sampling at 8 kilohertz. So 8 kilohertz means first they will pass it through a low pass filter, which is a 4 kilohertz filter, to make sure that nothing goes beyond 4 kilohertz to an A to D converter, which is sampling at 8 kilohertz. So after doing this, so if you have CD quality music, it will throw away all the spectrum which goes from 4 kilohertz to 20 kilohertz, because it wants to reduce the cost of the system. So they have decided they would not care about the quality of voice, they would rather care about the perception, because they believe people are using telephone not to listen to high quality music but just normal voice. So they do this, and interesting is, once they are sending voice. So this is Lahore, and there's a trunk line which goes from Lahore to Islamabad. Okay, and this is digital voice, and this is what they do. So first they send you your 8-bit of voice. A question that I was asked during question and answer session, looking at the sampled signal, can we know that the signal has? No, not at all. Absolutely no way. You cannot figure out that only if it is a sampled signal. You cannot figure out by looking at the time domain signal that it is aliased. Absolutely no way. Yes, if you listen to it, you may able to find that out. It's an image. If you view that image, yes, there is a way that you can figure that out. But otherwise, humanly, it is not possible for anybody to look at a signal. And as you must have done few examples, as Dr. Ali was telling me about a sinusoid being not sampled at right frequency. Okay, so this is a sinusoid. Instead of sampling it at Nyquist, you are sampling it at some other rate. So what will it will convert it into another sinusoid. And now you don't even have this knowledge that originally there was a sinusoid of high frequency. Absolutely no way for you to figure this out, because there is no way for you to figure this out. So what happens that you lose that information, and all you know is that there is a sinusoid which primarily